Hi, in this video I would like to introduce the solution to a very important definite integral that appears in many science and engineering problems. This integral is connected to the so-called Gaussian distribution, which appears in probability and random variables courses in the university. So this integral is in general given in the following format. This format is a definite integral from minus infinity to infinity of the following exponential function. This exponential function is impossible to integrate using the regular techniques such as integration by parts or integration by substitution directly. So we need to relate and use other ways to solve it. So the problem here comes from the fact that the exponential has a variable x raised to the power of 2. So this makes the calculation of the integral very hard using the regular techniques such as integration by substitution or integration by parts. And therefore we need to rely on other techniques using multi-variable calculus, and we use the so-called polar coordinate to solve this problem. So there are many ways to perform the calculation of this integral. So I will show you a couple of ways. The first one is using the traditional techniques and then double the integral. So first of all, we use integration by substitution to simplify the integral. So we can use, so this is method 1. So we have the integral, if you let u equal to x minus mu over root 2 sigma square. So you can notice that by squaring u, you get the x minus mu square over 2 sigma square. So in this case, if we call this integral I, let's give it a symbol I, then we are replacing this by u square. So let's find what will be dx in this case. So going back here, you can see that if you differentiate du by dx, what you get is, so that the derivative of x is 1 minus 0 divided by root 2 sigma square. So in this case, dx can be written as root 2 sigma square du. So now we are ready for substituting these two in the integral above. So what you get is I equal the integral of e to the minus u square times du, but there is a constant here which is root 2 sigma square, and of course we need to find the limits, so you can create a quick table here. So you have the value x and the value corresponding value y. When x is minus infinity, we know that this limit u becomes also minus infinity. When x is plus infinity, u goes to infinity. So they have the same limit. So it's minus infinity to infinity. So we have at the end root 2 square root of 2 sigma square integral from minus infinity to infinity e to the minus u square du. Now we need to evaluate this integral. So this integral, let's call it I prime. So the value I prime again is very hard to calculate, so we need to, the trick is actually to square I prime. So if you square it, it means that you get the integral minus infinity to infinity e to the minus u square du square, and this is just equal to integral minus infinity to infinity e to the minus u square du times integral minus infinity to infinity e to the minus u square du. And because they are two independent integrals, I can do a change of variable here, and make v equal to u. In this case, this becomes the integral of minus infinity to infinity e to the minus u square du times integral from minus infinity to infinity e to the minus v square dv. And when you multiply two integrals, since they are independent, you can combine them into a double integral. So that will be e to the minus u square times e to the minus v square du dv. So this integration is done over the two-dimensional space uv, so you can combine these together, u square plus v square du dv. So we can convert the uv space into r theta using the common transformation. So as you can see here, we are integrating over the whole two-dimensional space from minus infinity to infinity. So in this case, we have r between 0 and infinity, and theta between 0 and 2 pi. And we know that du dv is replaced by r dr d theta, and u square plus v square is just equal to r small square. So now we can replace this by r dr d theta, and replace this by r square and replace these integrals with the r limits and theta limits. So in this case we will have, so this is still I prime square, so I prime square is equal to the double integral from 0 to 2 pi for theta, from 0 to infinity for r e to the minus r square times r times dr d theta. And we can see that we can separate those integrals into two integrals, 0 to infinity r e to the minus r square dr times integral from 0 to 2 pi of d theta, and we can do integration by substitution. You let x equal to r square and basically you can solve for that, and the answer will be the integral from 0 to infinity of e to the minus x dx, and that will be, you can use the trick that you multiply a half minus half outside and a minus 2 inside. In this case we have the derivative of the exponent is outside, and this is just 2 pi, so this is simply e to the minus r square from 0 to infinity, and that will be equal to e to the minus infinity minus e to the 0, which is 0 minus 1 equal to minus 1. So that will be minus half times minus 1 times 2 pi, and that's just equal to pi. So in this case we have shown that I prime square equal to pi, therefore I prime is just the square root of pi. So if you go back here, we have that I, the original integral, is root 2 square 2 sigma square times I prime. So we know that I is equal to root 2 sigma square times root pi, which is equal to root 2 pi sigma square. And that's the final proof.